Hello, Section 8.3, Conditional Probability, Intersection, and Independence. So we'll have these two important concepts, conditional probability and intersection of sets, in order to prepare us for the dealing with the important role of independence of events in determining probability. Objectives. The student will be able to calculate conditional probability, and we'll be dealing with just that objective in this first video for Section 8.3. Student will be able to use the product rule to calculate the probability of the intersection of two events. The student will be able to construct probability trees, and the student will be able to determine whether events are independent or dependent. And so, as I said, we're just dealing with this first objective. The student will be able to calculate conditional probabilities, and then we'll move on to the next slideshow and video for the subsequent objectives. Consider the following problem. Find the probability that a randomly chosen person in the United States has lung cancer. Probability of lung cancer. So we want to know P of C, the probability of cancer. To determine the answer, we must know how many individuals are in the sample space, N of S, that is, number of people in the U.S. Of those, how many have lung cancer? Those would be the so-called successes. And then the ratio of those successes to the total number of possible outcomes. The ratio of the number of people that have lung cancer to the number of people in the sample space, that is the total number of people in the U.S. Okay, so let's compute the ratio. Now, whatever you think that ratio is, let's change up the problem a little bit. What if you knew that the person smokes? So now we had a probability in mind, very low, for probability that anyone you pick out in the U.S. has cancer. But now, what if you know the person smokes? Do we expect the probability of cancer to be the same? Probably not, although the cigarette manufacturers may disagree. What we now have is called conditional probability. On the condition that the person smokes, what now is the probability of cancer? So P of C given S. So we have this vertical bar, which means given that. Probability of cancer given smokes. It means the probability of lung cancer assuming or given that the person smokes. Given that the person smokes. The probability of having lung cancer given that the person smokes is found by determining the number of people who have lung cancer, so the count of all those people that have lung cancer and smoke, and divide by the number of smokers. Because now you know that the person smokes. You're given that. So now that is like the universe. Okay, so probability of lung cancer and smokes. So the person has to smoke and have lung cancer, divided by the total number of smokers. Okay, so these two sets, there is obviously some overlap there. There are people with lung cancer. I guess there are people with lung cancer that don't smoke. So I guess that there are people over here. I believe that there are. And people who smoke, there are certainly people who smoke who do not have lung cancer. But then there are people who smoke and have lung cancer, and that's in the overlap. But in this situation, we are concerned with just the universe of people who smoke, right? That is the number of smokers is that's the universe. That's it's out of that group that we're trying to determine the probability of lung cancer for them. And so it's kind of like this region over here to the left doesn't really exist. Okay, so this isn't here, and we're just restricting our attention to the people that smoke. It's a world of smokers. Everyone you meet every day is a smoker. Now, given that, what portion of that group is in the lung cancer population? Okay, so formula for conditional probability. Derivation. Probability of lung cancer given smoker is, as we have seen, the number of people that have lung cancer and smoke divided by the total number of smokers. Now, we're going to get another formula not involving n, but involving p, the probability of. These both involve n. So we're going to divide top and bottom, dividing numerator and denominator by the total number, n of t, no number of elements in the sample space, total. That is number of U.S. citizens in this, or U.S. Number of people in the U.S. That's the total number in the sample space, n of s. That allows us to express the conditional probability of L given S, lung cancer given smoker, as the quotient or division of the probability of L and S, L intersect S, divided by the probability of smoker. So divide top and bottom by a total number of people in the U.S., n of t. You know, what's that number? It's over 300 million. But what have we done? Now we have a probability. Okay, that's probability of smoker right there. Number of smokers divided by the total number of people. And in the numerator we have a probability. Probability of lung cancer and smokers. You know, the people about whom both of those things are true is a certain number, and divide that by the total U.S. population, and you have a probability that the person is both a smoker and has lung cancer. Notice how I interchange those two things. We're actually going to do that in the next section. So, by the way, okay, out here in the margin, I'll make a comment that this probability here is the same thing as probability smoker and lung cancer person. Same thing. It's just the number of people about which both things are true. But now we do have another formula for cancer. Given that you're in this world of all smokers, generalizing, we have a formula for conditional probability. The probability of an event A given that event B has already occurred or is assumed to hold is equal to the probability of the intersection. Okay, intersection, that's the and right there. The intersection of events A and B divided by the probability of B alone. And that's a formula right there for conditional probability. Okay, and we're going to see other forms of it, but you have to understand that. Where, of course, probability of B is not equal to 0. Now, we mentioned intersection of events. And so obviously we're thinking, intersection, what does that mean? Intersection refers to sets, right? The set of all elements in the one set and in the other set. And so we must be thinking of events as sets. And often that is the way it's done. Event is a set, all subsets of interest of the sample space. Okay, so here's an example. You're at a college and we're interested in two majors, nursing and engineering. The number of students enrolled in each program is given in the table on the next slide. The row total gives the total number of each category, and the number in the bottom right hand cell, bottom right, gives the total number of students. A single student is selected at random from this college. So you're at the college, one student selected at random. Assuming that each student is equally likely to be chosen, find. And we're going to have four things that we're going to try to find. Probability of nursing, and then three other ones. Okay, so here's a chart showing the different populations. These might be in hundreds or in thousands, or maybe they're just 150 people at the college. So with this info, what is probability of nursing? Well, all the nursing people are in the top row. There are 100 total. That's the number of successes divided by the total number of possible outcomes, which is 150. Okay, so that's your universe of probability. Well, it's going to be 100 divided by 150. That fraction reduces to 2/3. So probability that your one student that you picked is studying to be a nurse is actually 2/3. Probability of grad student. Well, grad student, that's the red column there. And of course, there are two factors, two majors, nursing and engineering. So we're at nursing and engineering U. You've heard of that one, right? And there are undergrads on campus and grad students on campus. Well, what's the probability of grad student? That's the red column, and there are 60 of those total. Divide that by the total number of possible outcomes, 150. And you have 60 over 150, a fraction which reduces to 2/5. So probability that you just grab someone on campus and that person is a grad student is 2/5. Probability of nursing and grad student. Well, you can see that in the table, that's the intersection of the nursing row and the grad column. and there are exactly 47 people that are both a nursing student and a grad student. So that out of the whole 150 is the probability of nursing and grad student. So it's easy to get these little pieces by looking at the chart. Probability engineering and grad student. And you can see that there are 13 of those people. 13 of those people. Not too many. And we'll divide that by the total number of possible outcomes, 150. But now we've got some pieces, and now let's consider further another problem. Given that an undergraduate student is selected at random, so same experiment. I'm sorry. Not completely the same. This time we know that it's undergrad. It's an undergrad. What is the probability that this student is a nurse? Okay, now here's where we have to use our imagination a little bit. And once you learn to do this, you'll never have a problem with it. Probability of nurse given grad student. Okay, so let's think about this. We're to find probability of nurse given grad student. Okay, that means I'm sorry, undergrad. My bad. Let me fix this. It's an undergrad. She or he does not have hers or his bachelor's degree. So he or she's an undergrad. And given that, what's the probability that the person is a nurse? It's probably going to be high. So let's see. Probability nursing student given that the student is an undergrad. Well, that means now that only this column, that's the universe. That's all that matters. We are going to restrict our attention to, and so 53 successes, 90 possible outcome, and 53 90ths is probability of nurse given undergrad. Given that an engineering student is selected, okay, so just the geeks are allowed now. That's the universe. Find the probability that the student is an undergrad. Okay, so now it's probability undergrad given that you know the person is a geeky engineering student. Well, we restrict our attention just to that engineering row, and now it's like this row of nursing students doesn't exist. It's only the row of engineering students that exist. And in that universe, what's the probability of undergrad? Well, 37/50ths. What's the probability of undergrad given that we're in the universe of engineering student geeks? 37/50ths, or 0.74. That's the probability of engineering undergrad given engineering. And that will get it done for Objective 1, calculate conditional probabilities for Section 8.3.